MacMaths, let's do some maths today. Okay guys, today I want to look at a simple introduction to vectors. This is lesson 1, it's AS Maths, pure maths. It's not really any different than perhaps what you've done at GCSE. So I want to start off by talking about that really. If all the vectors you've seen is at GCSE, then you are used to seeing these little arrows with the lowercase letters next to them and following these little arrows and adding them up round geometric shapes. And that's our little intro to vectors at GCSE, and actually the A-level starts off the same way. What these are setting you up for, and I'll just take a minute or two just to give you the bigger picture. What are these? These are setting you up for getting you used to vectors for when we start to apply them to real life situations. You see, vectors are very useful in life. They have two distinct properties. So if we look at this little vector here, vector A, that I've drawn, it has those two properties that I'm talking about, is that it has a distance. It's a distance from here to here. On this one, using Pythagoras, because I've drawn it on a little grid here, it's the hypotenuse of a triangle that is 1 along and 5 up. So 1 plus 5 squared, 1 squared plus 5 squared is 26. So this is the square root of 26, this distance. So that's about 5.1. So this has a distance about 5.1. In mathematics, in mechanics, we call that a magnitude. This vector has a magnitude of 5.1. That's its first property. The other property is, of course, it has a direction. It's running in this direction. We can work out and describe that direction using angles. We know it's 1 along and 5 up. If we use the inverse tan, because that's opposite over adjacent, 5 over 1 is 5. The inverse tan of 5 is about 79 degrees. So this vector has a magnitude of about 5.1 centimeters in this case, and a direction of 79 degrees approximately to the horizontal. We could change that into a bearing. The bigger picture, of course, then we can use this in mechanics and engineering and further on at A-level, and that's what we're going to use it for, to represent other things, more important things than just a simple little line. Things like a velocity. A velocity is a speed that has a direction. So we could describe a car using this vector. If it was a car, then this car would be travelling at 5.1 meters per second, say, in a direction of 79 degrees to the horizontal. You know, we did that on a grid. We could say it's just heading off just right of the North Pole. We could give it, you know, coordinates on a globe or whatever. Okay. If it was a force, we could say someone is pushing with 5.1 newtons, or a force is being pushed 5.1 newtons in this particular direction, 79 degrees to the horizontal. Okay, so we can use it for forces or velocities and other things as well. Okay, so that's where we're going to end up. You may have seen them like this at a very sort of simple, I've forgotten to draw this underneath my piece of paper. You may have seen them drawn in this way, where you're given 2 points and you're told that if you go from A to B with a little arrow over the top between 2 points, then that's described as A, and you have to draw it you know yourself. So you might have seen it, that sort of thing at GCSE. Where's my little cloth? Can't find my cloth. Where is it? There it is, got it. And again, just going back to the bigger pictures, you know, you may have sort of, you know, looked at sort of bridges and the way that they sort of design bridges. Oh my word, that's an awful bridge. But before they, there's a river underneath, okay, and a bus goes across. You can see I'm no artist. Before they build a bridge, of course, they don't just build it and send some people across on a bus to see whether it stays up or collapses. They do the maths on it, and they're looking at the forces, you know, along all of these spans and support beams and so on, to see whether they can do that all by vectors. And that's the sort of maths they do. The planes flying around in the atmosphere, in the air. My word, I'm struggling now. Planes flying around, they they're all travelling at different velocities, going in different directions, and the programs that run the air traffic control that stop all of those planes crashing into each other are actually run on three-dimensional vectors. That's what the programs are based on. And that's where we look at three-dimensional vectors at A level as well, and effectively we look at that sort of thing, and this is the sort of start of that. So let's have a look at some simple rules of vectors, and we'll look at some parallel vectors as well. And it's just a very sort of quick one. You've seen this before. We've got this vector A here, so it's this long and it's running in that direction, and so we can actually draw that anywhere as long as we've got a length running in that direction anywhere. Then we could describe that. Then if we describe this one as A, then we describe this one as A. If it's twice as long in that direction as this one is, you can see, then we would describe that obviously as 2A. If we do it the other way around, okay, so going back the opposite direction but the same length, then we would describe it as, there you go, I've done it there, describe it as minus A. And we add them up in maths, or we can add them up in maths. So those are those two vectors I've looked at there, my A and my B. And if we go an A and we add the B on the end, we get A plus B. So we describe this vector here as the vector A plus B. I've got that somewhere. There it is. There's the vector A plus B. If we drew the B first and added the A on top of that, at the end of that, it gives us the same vector A plus B. B plus A is A plus B. And that's because 2 plus 3 is 5, 3 plus 2 is 5, isn't it? If we did takeaways and did minus B plus A and so on, you've got to be a little bit careful. It does give us the same magnitude, but it's just in the opposite direction. How do we know when things are parallel? They're just multiples of each other. So here I did 2A's and 2B's. So this is 2A plus 2B. If I factorise this, I get two lots of A plus B, and you can see the A plus B and the A plus B, two lengths of A plus B, and we look at that and you can see that this one, you move it over, it is actually sort of parallel to it. I know I twisted it a little bit there, okay, but it's twice as long and it is just parallel to it, okay. The exercise actually finishes with a question, and I'll do that one first. Question number 11 it is actually in exercise 11A. So this is the very first one, and it is just an exercise where you're moving around sort of shapes. I'll show it you in a second. I'm only going to do one question from this exercise. So question 11 from 11A, the last one, it says the vectors 2A plus KB and 5A plus 3B are parallel. Okay, so it says there, obviously find the value of K. Well, there's different ways of doing it, but if they're parallel to each other, then they're both a multiple of each other. So if we look at 2A plus KB, and underneath that I put 5A plus 3B, we've got, it's like similar shapes, isn't it? How do we get the scale factor of going from 2 to 5? Well, we times by 2.5, 2.5. So if we go back the other way, we divide by 2.5. So if we divide this by 2.5 to get 2, and then divide that by 2.5, well, 3 divided by 2.5 would give us the value of K, and 3 divided by 2.5 actually gives us 6/5 or 1.2. But in maths we like to use fractions, don't we? So 2A plus 6/5 B, that's the value of K, and that is parallel to 5A plus 3B. Now we can see that more obvious actually if we factorise both of these, and what I'm going to do is I'm going to factorise this one by halving it all. Okay, if I halve it all, I'm dividing it by 2, aren't I? So it's going to be 2 lots of A plus half of 6/5, of course, is 3/5. Oops. Let's get that in the bracket. 3/5 B. So halve all of that, it's the same as that, you can see. Just the same, it halved it, so factorised and taken that 2 out. If I take out 5 of this from this one, A plus divide that by 5 is 3/5. And there we go. You can see it's the same. It's the same vector. This is 2 times the vector A plus 3/5 of B, and this is 5 times the vector of A plus 3/5 of B. So they'll be running in the same direction. Even if one of these was negative, it's still a factor. So minus 2 lots of this is just that vector going twice in the opposite direction. It's still parallel. So even when they're negative, they can be parallel, can't they? Just running in the opposite directions. Okay, we'll look at just one question. It's just one I've made up myself, just from having, 25 years of seeing these sorts of questions, these simple ones, at GCSE really, but they're in the A-level textbooks as an introduction. So this one here, and I'll just go through this one with you. A parallelogram A, B, C, D, where A to B we can write as lowercase a and A to D lowercase b. Well, if you're doing a question like this and they give you a parallelogram or a shape A, B, C, D, always go round. I tend to go round clockwise. So that is their intention, is to go, you go from one to the other. Anti-clockwise or clockwise will give you the same answers. But I'm going to go round clockwise. So I'm going to go A to B to C and to D, and there's my parallelogram A, B, C, D. So I've drawn that. Now I'll look at this. A to B, let's label it up now. A to B, so there to there, we call that an A, and A to D, that would be a B. Now this is interesting. I've used a language that you see in textbooks. M is the midpoint of BC. BC, so the middle there. Let's label that point there M, and P divides DC, so it's somewhere, P is somewhere along DC, such that D to P to P to C is at the ratio of 2 to 1. Well, 2 to 1, you often get these ones as well with vector questions like this. 2 to 1 is 3 units altogether, so if we divide that up into 3 equal parts, DC, and then 2 to 1 is 2 along, so P is here. Okay, so DP to PC is 2 parts to 1 part. You can see that. That would be 2 parts and that's 1 part. Okay, now we've drawn our diagram from the rules it's given us in the question. Find AC. Okay, so A to C, well, you can see that's an A, and from there to there is the same distance and same direction as that, and we know that's a B, so that's also a B. So this is an A plus a B. So A plus a B. D to B in that direction, D to B here is minus a B, because it's the opposite way, plus an A. So that is minus B plus an A. Okay, minus B plus an A. We are mathematicians, so we don't like these floating minuses, and we do tend to like things in alphabetical order as well. So we can write our plus A at the start. We don't need to put the plus on there. By default, we just write it as A, and we've got a minus B. So much better to write that as A minus B. Okay. A to M. A to M, well, we can get from A to M by going up an A and along half a B. So that is A plus half a B. That's that one. B to P. Okay, so that's a B along there, isn't it? So that's a B. And we're adding this bit on. So we're going to add on, now I've put that there, I shouldn't have done that really, but we're going to add on this bit. And this bit here, you can see, is a third of the way along this line. And this line from there to there is actually minus A. That is A, this is minus A. So it's minus a third of A. Now I could write alphabetical order and that first minus a third of A plus B, but I don't really want that floating minus, so I'm going to just tidy it up and put B minus a third of A. And I'm going to finish with PM. So P to M, well, the quickest route is to go to up to C and then along. So that's a third of A because we're going in the positive direction. A third of A, and I'm happy there because I've got my A first, haven't I? And then minus half a B. And there we've got it. And we're back to M. Incidentally, just looking at this one, just thinking about something to add on before I hit the stop button. If I wanted to go from P to C, I don't have to go there to there, which is from P to C is, you can see, is a third of A. But I don't have to go that route. I could go a different route. There's lots of different routes. I could go from there to here and then back, and I've got that. I've got PM. It's that. And I'd go from there to there. So I'd go all of that distance, and then I'd go plus half a B back here. And minus half B plus half a B, you can see, just leaves me with a third A. In mathematics, we call that distance there the displacement. In mechanics, we certainly do. Displacement is just the distance from the starting position, no matter what you do in between. And the displacement between those 2 points, however you get there, is a third of A. So even if we went all the way round to get from P to C, well, let's do that. If we went all the way round the long route, we're going down there, which is minus 2/3 A. We're going a minus B along there. We're going a plus A up there. And we're going along there, which is a plus B, aren't we? Okay, so if we went the long way round, we would do minus 2/3 A, minus a B, plus an A, plus a B. There. And you can see there that minus B plus B is 0, so that cancels it out. And minus 2/3 A plus an A, or an A minus 2/3 A, of course, is a third of A. And there we have our displacement, the gap between P and C, going in that direction. That's enough now. You should be set up now for, if I just have a look at this, you're in exercise 11, and where are we? At the start of 11A, you can see there's the question that I did, but 11A is just, it's just going around these little shapes, and you can see one of the ratio problems there, and it's all similar to what I've just explained, and it's just a little intro into vectors. So have a go at those, 11A, do a few of them, and it gets a little bit tougher as we move on, and it does end up, even in this chapter, looking at, I think, velocities and forces and so on. So we'll get on to those, and we'll be doing a lot of those next when we cover the mechanics course. Okay, so have a go at those today if you can. So it's 11A from the Pearson, the Year 1 AS Pure Mathematics book. Okay, that's what I'm using. Okay, thank you.